Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so this is another session on systems. I'm still Dennis Gannon. And we have 3 talks coming up, and the first one is on relational data markets in the cloud. Magdalena Balazinska is the speaker from University of Washington. And so I'll let you go right ahead.
Right. Thanks, Dennis. Thanks, everyone. This is work that we are currently doing at the University of Washington, so joint work with Bill Howe, Dan Suchu, and all the students in the database group. And this talk is actually going to be very different from the talks we've heard so far, because I'm not going to talk about data analysis. Instead, I'm going to talk about the price of data, buying and selling data in the cloud. It's also a very different talk in the sense that this is a project we are just starting, so it's mostly kind of a vision forward and raising questions more than answering these questions. So what are we talking about? So data we know is valuable because people are collecting a lot of data and are analyzing it. But in the real world, there are actually real people who are willing to pay real dollars to acquire data. For example, if you're interested in real-time stock prices, you can visit this company and actually pay a subscription of up to, they have different levels, up to $35,000 a year, and you can get that data. If you're interested in parcel information, these are kind of land parcel information, you can also get that data online and pay maybe up to $60,000 a year for the information. So once again, data has some real dollar value, and people are willing to buy and sell data. And the question that we started to ask in our group is, well, clouds are really great at helping people just put their data in one single logical location and have access to this data. So can we use these clouds to facilitate buying and selling the data? And the fact is that, yes, this is the case. And in fact, there are several data markets that are already emerging in the cloud. So the first to actually here, one is actually Azure has now a data market where one can buy and sell data. There's another company, InfoChimps, that also has a data market where people can come and buy and sell data. The other 2 are more like data providers online, but they're still interesting, so I've thrown them up there. So this is very exciting because we have this opportunity in the cloud where people can get together to exchange data. So let's take a look at one example, which is the Azure data market. So if you go to the Azure Data Market website, you have a very simple interface that says, this is one-stop shopping for data. You can search for whatever data you want or browse. Let's say we are going to look for weather imagery data. So here I found a data set, and as you can see, I have a choice. I can subscribe depending on how many requests, what heavy use I want to do of the data. I can either pay, if I just want to test it, I'm not going to pay anything. Otherwise, I pay increasingly large amounts for the data. So of course, being an academic, I chose the cheapest option, but I just needed kind of the one query for the demo here. And once I purchased the subscription, I was able to visit this data set, and I could ask queries over the data. In this query interface, what I can do is simply specify some geographic location. In this case, I'm giving a Bing tile number, but there's also another query that allows me to give the latitude and longitude and get the corresponding tile, which is going to look like pretty much this type of weather information that I can overlay on any map. So this is great and exciting. It's already available. So what are the technical challenges? Well, we've identified and started to think about 2 of these challenges. One is simply, how should I price data, right? Data is this digital good, which means it's hard to price it on how expensive it is to produce it because I can always create as many copies as I want pretty much for free. So what should be the right strategy here? And second, if we are going to have these data markets, can the database community provide some tools that are going to make these data markets perhaps more efficient, more useful, and so on? So let me take a look. Let's kind of go over these 2 challenges. So in terms of pricing data, there are currently 2 models. The first model is the one that I showed you for the Azure data market, which is subscription-based. For each data set, the user has the option for 1 or more subscriptions. The subscriptions indicate how many transactions one can do per month. A transaction means simply running a query that returns up to that returns a certain number of records, each batch of 100 records counts as one transaction for my total monthly payment. An alternative way to sell data, which is actually pretty, maybe what we would be more accustomed to, is simply to pay for the entire data set, just acquire a whole database. Possibly, if I don't want to spend the money on the whole database, I can pay less to get subsets of a database. This is the example where Custom Lists is actually selling data in this fashion. Here's an example of, they have a database of Canadian businesses with lots of information, some email addresses, contact information, and so on. And if I want to buy the whole data set, well, I have to pay $400. If I'm not interested in all of Canada and I don't quite have $400, well, maybe I can pay less, only $200, and get the information for one province. So what are the issues? So this seems to be, reasonable pricing schemes. Why is this not enough? So there are several reasons. The first reason is that if I have these subscription-based or lump sum payments, this is really inflexible. In the cloud, what I would like is have everyone contribute data and other people buy this data to build all kinds of sophisticated, fancy applications. So I want to give them as much flexibility as possible. If I use only this lump sum payment, then an application developer has to buy only the specified views or subsets of the data. If I buy a subscription, currently I'm only allowed to ask these very specific questions, these very specific queries on the database. I can only tweak the parameters for these queries. I cannot ask arbitrary queries on the data. But is there a fundamental reason for doing so? Or could we develop pricing schemes that would allow a user to ask any arbitrary question and for the system to automatically derive some price for the results of that query? The second challenge is that it's not clear how to price updates in a lump sum or subscription-based model. What if the data changes? Do I have to repurchase the entire data set? Can I purchase, if I use a subscription and I know the data changed, I have to rerun a query. I don't want to pay for the duplicate records that I already have. I want to pay only for the new records. And actually this goes further. You might say, well, maybe I can live with these challenges, but there are worse problems. One is that these data pricing schemes can actually have pretty bad properties. So let's revisit the subscription choices that I had for the weather data at the beginning of the talk. So here are the choices that I had, and I went for the cheapest one. But let's say that I actually really need to ask in the order of 10,000 queries per month, but I don't quite have the $120. But this is the cloud. What can I do? Well, you can all kind of imagine. What I can simply do is I can pretend to be 4 different users with 4 different subscriptions, and I get my 10,000 queries, my 10,000 transactions for free. So this is pretty kind of we claim this is a bad property, and we would like some ability to avoid these types of bad properties, or if they arise, at least be able to notify the data provider that such a thing can arise. There are several additional challenges. One is that it's not clear how we can price the output of a query that correlates different data sets, especially if these data sets are owned by different users. Currently, I typically will be able to buy a given data set or run queries that run over one data set, or definitely run over data owned by a single person. So in general, there really isn't a way to price data in some principled fashion. So let's take a look at a couple of solutions. These are by no means, the final answer. These are just kind of 3 different ideas that we have for alternate methods of pricing data. The first one is what we call pricing data using the price semi-ring. Second one uses provenance expressions, and the last one is view-based pricing. I'm going to present these 3 in the next few slides, but our goal is to really address these pricing challenges, enable fine-grained pricing, arbitrary queries across different data sets, and avoid having bad properties. So here's the example of what we call pricing using the price semi-ring. What I'm going to do is going to be quite different. I'm going to start with my database, which has these relations R and S, so the tables R and S. I could imagine that R is perhaps my list of companies, S is maybe the list of locations where they are, and what this query is asking for is to join these 2 tables together. So perhaps what I want is find for each company the city where it is located, and I only want company in the province of Alberta, And I want for each of these companies to only see the company name and also the city where it is located. So I have my query queue. In the top right, I have my tables. What we would currently do is that we would have this query, and maybe we would allow the users to change the parameter, which is the province that they're interested in, and we would have them pay some predefined cost. But I would like more flexibility. I would like to not only support this query, but also support other queries. So the alternative pricing model is that I'm going to price my individual tuples. So here at the bottom, I have prices for my base data. And I can assign different prices for different tuples. Perhaps some companies are extremely popular. So maybe I want people to pay more if they ask about Starbucks or McDonald's. Maybe they pay less if they ask for universities or something less interesting. And what we want is to, once the users do this, we can define a semi-ring which will allow us to say how do I combine these prices during query execution. So perhaps what we suggest here is every time I'm going to join tuples, I'm going to add the prices of the tuples involved in the join. And if I'm going to do duplicate elimination, well, I can take the minimum of the two prices that give me my answer. And here's the example of the computation for this specific query. And this is pretty nice. So there are several benefits to this, this pricing scheme. One benefit is that it allows me to assign different prices to different tuples, so I have a lot of flexibility. Users can ask any query because now I have a mechanism to go from the raw data all the way to pricing the output of a query. I don't have to predefine a set of queries. I can compute prices across data sets, across data owners. And I can avoid different bad properties because now the cost that I have to pay depends on the tuples that are involved in my query computation. But one of the challenges is that this still constrains what I can do. For example, I can't have the possibility with this technique that if you buy all of the company information for all of Canada, you end up paying less than if you only buy you buy less per output tuple than if you only buy, for example, the information for one province. The previous scheme does not allow me to do this. So can we do something better? One alternative is what we call price using provenance expressions. So here, same query, same data set. But what I'm going to do is not automatically combine the prices in some predefined way, but I'm going to compute for each output result the provenance, meaning what tuples have been used to contribute to the answer. And actually, I can actually encode not only the set of tuples, but also how these tuples were combined to form my final answer. And now what I can do is instead of computing the prices as I compute the query result, I can accumulate and for each result tuple have this actual expression that captures the provenance of that result. And then I can apply some pricing function to that expression. So here, one example would be maybe I'm going to simply add the prices of all the tuples that went into computing the result. And then maybe because in this case, the user used a big fraction of the database, I can apply a 25% discount to the data. So what is nice with this strategy is we can do something much more powerful than in the previous strategy. I can still support arbitrary queries over the data. I can still combine data from different providers. So I still have a lot of the benefits as I had before, but a lot more power. We still have to be careful. This is something still an open question, whether I can ensure that I don't have any bad properties that can arise from these more complicated pricing functions, or at least if I can verify that these do not occur. A bigger problem, or at least a problem that is equally as important, is that this can be extremely expensive. If I have a complex query, the lineage of each of my tuples can be quite a big expression. And computing these expressions, storing them, and carrying them around might end up being quite expensive. So I might have a lot of overhead just to compute the price of a query, which is not necessarily desirable. So let's take a look at the third pricing model, which we call view-based pricing. So here the idea is very different. Instead of having the user price the input data, the base tuples, we're going to stick to something that users are more accustomed in doing today, is that they're going to specify these views, and they will give us the price of the different views. For example, my database has all the businesses in North America. If someone asks for all the businesses in Canada, I want them to pay $600. If they only ask for one province, I want them to pay $300. If they only ask for one type of business, maybe shell businesses or Starbucks or others, I want them to pay $50. And now the question is, can we start from these specifications, which do not cover all the cases, and can we automatically compute the price of a query that asks for something different over the same data set, such as find me all businesses that have more than 200 employees? So the idea here is that we're going to do this view-based pricing. So the way to think about it is that the information that the user provided us here, these are a lot like constraints. I know that no matter what pricing function I choose to apply, it has to be the case that these queries will have the following prices. These are my constraints. But given these constraints, I can do almost whatever I want to figure out the prices of the other queries as long as my pricing function respects these constraints. I can even add additional constraints maybe. I can say that the total price of a database might have some cost or whatever other constraints we might want to think about. Currently, we are thinking of two methods for using this type of pricing. One is to simply start from maybe a price semi-ring or some other way to take the base tuples and combine their prices to create the result. And simply say, well, if that's going to be the pricing function and I have these constraints, let me reverse engineer the original base tuple prices such that if I apply this function, I will get these results for these views. So I can say, and while I do this, I will probably have several options in how to price the base data in a way that satisfies these constraints, so I can choose to optimize some function. Perhaps I want to maximize entropy, which means I want the prices of the base data to be as uniform as possible, subject to the constraints that the user has provided. Maybe I want to look at how heavily users access different parts of the database and somehow optimize user utility subject to the constraints that the user specified on some of those queries. So this is one approach that we are studying. One of the great benefits of this type of pricing model is that it can be very intuitive for users because they are accustomed to saying, for the following high-level queries, this is how much I want my users to pay, and now the system can automatically derive the price for other questions. Of course, there can be some unexpected consequences that some queries might end up costing very much or very little, not what the user intended. The alternate strategy to computing the prices would be to maybe compute the prices of new queries directly without even going back to the raw data. And once again, here we have the choice of how we compute the price of a query as long as we respect the constraints that the user specified. And we might want to add some additional properties. Perhaps I want to make sure that if I compute the price of a new query, it is the case that if this query can be derived from other queries that the user specified, well, the price is not higher than the price of these other data sets. And these are still things that we are exploring. And as I mentioned, many benefits to this last pricing scheme. It's going to be, it also allows arbitrary queries over the data. We can compute prices over different data sets. It's very, it's kind of in a funny way. When I price input data, it can be pretty easy for a user to decide on the prices of the raw tuples in the database. On the other hand, it's nice for a user to be able to create these different views and versions, saying if I have my business users who are allowed and able to pay lots of money, they will ask for the entire data set, so I want them to pay a lot of money for these types of queries. If I have my random people who are just browsing the web, I still want to attract these customers and maybe give them subsets, tiny subsets of my data for pennies. And this allows this type of specification on top of the database. However, it's still not clear what would be the right way to then, from these constraints, as I say, compute the price for other queries without any negative side effects that might be unintended. So these are kind of the main challenges that we're looking at in terms of pricing the data. We're also looking at what other tools do we need to support a data market, in addition to simply models for pricing data. One tool is, of course, going to be some efficient way to compute prices. As I mentioned, if I'm going to use a technique that requires me to carry around these provenance expressions, this can be very expensive. So how can we develop fine-grained pricing that is intuitive, that is flexible, that is powerful, but can also be computed very efficiently? Perhaps I can do some pre-computation ahead of time for different views, different pre-computed materialized views, such that when users come and ask different questions, I already have a lot of partial pricing information computed. This is still an open question for us, something that we're exploring. Another question, as I mentioned, in today's data sets, in today's pricing models, it's unclear how to price updates. Well, can we provide a tool that will help people ask questions and maybe register and saying, well, this is a query that I run. If there are updates, please notify me. And we can efficiently figure out that there are updates to a previous query and figure out how to price only the data that appears in these updates, such that people only pay for the new information. One of, I think, the most interesting and most important tools will be a pricing advisor. Can I build a tool that will look at the models for pricing and will help people figure out, are there any bad properties such as arbitrage that can occur with a given pricing scheme? Can there be any odd side effects if, let's say, I use the view-based pricing and I specify the price of a couple of views? Is it possible that now there's some tuple in the database that becomes free or that becomes extremely expensive? If I have some goals as a data provider, I want to make a certain amount of money and I have a workload, can I use this pricing advisor to help me figure out how to price my data in order to accomplish and achieve these goals? If I'm a user and I'm about to ask some questions on a data set, can I have a tool that will help me estimate how expensive my query is going to be? And this is hard because if I run an arbitrary query, we know in databases that it's hard to estimate the size of the result. It's hard to estimate what is going to be in this result, which means it will be equally hard to estimate the price of a query result. So I think there's kind of a rich area of future work in figuring out how to build such a pricing advisor. And of course, what we would like is some sort of price over query optimizer that if I'm a user using this Azure data market or some other data market, and I would like to run a query that combines different data sets, but perhaps there are multiple data providers offering weather information. Perhaps there may be multiple data providers offering information about businesses. Can I have an automated way to figure out what's the cheapest way to answer my query given the current prices that are offered? And this is further complicated by the fact that most likely the data sets will not be comparable directly, because one data set may be cleaner than another one, may be more complete, may have more information in it. The other data set might be more ad hoc, but maybe has other attributes that the first one doesn't have. So this will be an interesting challenge given the incomparable kind of nature of the different data, yet likely overlapping nature of that same data. So this is kind of, just to wrap up, what you're looking at is something very different. We're interested in kind of combining cloud computing, data management, and economics. What you are looking at right now is this idea of buying and selling data, building data markets in the cloud. And in particular, if we build these data markets, how should we price the data? What tools should we provide for users? We don't want to dictate the prices. We just want to provide tools for users to play with these pricing mechanisms. And if we do this, what other tools do we want to provide to make such data markets more successful? We basically have no website. We just have a URL. So please visit us soon. We actually have, I forgot to mention, a paper coming up at the next VLDB conference, which is a short vision paper on this topic, and hopefully more information coming soon. So please visit us as more information becomes available. Thank you.
So let's thank Magdalena. So we have time for some questions. There's one right there.
Hi, Ken Yoakum, UCSD. So this is kind of a, I don't know, maybe this is a lowball question, but what about doing this for unstructured data and UDFs, right? And sort of along those lines, have you thought about flipping it over and not just pricing like the input data, but maybe the transforms themselves, since you may not have, sort of the nice properties that relational algebra gives you? Thanks.
That's right. So we did. So this is a great question. The question is, what do we do in case we have unstructured data, user-defined functions, and not these nice relational operators? And we are thinking about this. And one way to, we don't have the final answer yet, but one solution or part of a solution is to have a way to price transformations. Any transformation that I apply, I might have the user say, well, this user-defined operator really has the top-notch, this is, Mike Franklin's top-notch machine learning algorithm, very expensive. This is, out-of-the-box machine learning, well, not so expensive. So maybe we could have these prices attached to the transformations such that the price of the output is the price of the input plus some extra cost due to the transformation. Not necessarily because it's expensive to run, but maybe because it has some interesting proprietary knowledge. So we're thinking about this, but we're not there yet. And this is a great question. We did not think about unstructured data yet.
Stefan from Singapore. I'm wondering, have you done some case studies to figure out how much the data providers and the users are valuing or are pricing the raw data or the results from queries? Do you have an idea? It might not be at all in that way.
So we talked to some data providers, and some of the answers we heard was that people definitely like predictability. So if you're going to come up with some pricing models, they want to be able to predict how much money they're going to make or how much money they're going to pay per month, which is one desired property of any pricing scheme. But they also did complain and say that they would like to have something more flexible as a way to figure out what is the right pricing model for data online. So we're kind of trying to achieve both goals, provide the flexibility, and yet predictability was one of the key challenges and requirements that we've heard from people.
All right, let's thank Magdalena one more time. Thank you. So if we could get our next speaker down here. So while they're setting up, I'm going to introduce the speaker. The talk is titled Into the Blue, Streaming Data Processing in the Cloud. And Stephen Wong from Rice will be giving the talk. And Christopher is going to be operating machinery, I think.
No, he's talking to.
Oh, okay, you'll be talking to. All right, very good. And in the display, display over here, there's the timer, and I will reset that.
Signal. Yeah, we're closer to the outside. Okay. Like you said, I'm Stephen Wong, and this is a project that was done at Rice University by my software engineering class. Christopher Alme, Christopher Nunu, who's here, Dennis Chen, and Stanley Roberts. two of which are coming to Microsoft, including Christopher. Well, both Christophers are coming to Microsoft. All right. Last year I came to Cloud Futures, and I watched, listened to all the talks, they were great talks, and what I noticed was there seemed to be this gaping hole in the sorts of things that were being done. In particular, what I didn't see last year was much work being done on real-time streams through the cloud. There was a lot of work on where we take data, we move the data up the cloud, we process it, we come back with an answer. And maybe we're doing that many times, maybe we're doing that iteratively, but we're always taking bunches of data, putting it up there, processing it, putting a bunch of data down, okay? It wasn't a stream of data, okay? So I said, well, why don't we do this? Why can't we think of the cloud? We've got this huge processing capability up there, process multiple streams, take multiple streams of data, continuous streams of data, pump them up to the cloud, process them up the cloud, and then pump multiple streams of data back down to the ground, okay? We've got this huge processing capability up there. And the difference was I really wanted to think of elasticity less in terms of, okay, I want to, pile on more of the same compute capability to, handle more stuff at Christmas time or whatever, but to really think of it in terms of changing what I'm doing up in the cloud by adding or subtracting capabilities up in the cloud to change what I'm doing with these streams of data, okay? So to think of elasticity in terms of dynamic configurability rather than just adding more or less capability to my system. There are a lot of practical uses for this sort of system. It's quite different than the type of things that we've been hearing about so far today. For instance, it's kind of scary, but there is no way of tracking where all the airplanes are in the world right now. They're all local, but all planes have are streaming data. They all have transponders on them. Why can't we take all that data? Those streams of data, feed them together, and have something that is producing all the various views that are needed to understand air traffic at any given moment. Okay, for each of the local controllers, for the nationwide controllers, all different ways people want to look at them. Down in Houston, certainly we're very concerned with things like disaster preparedness. We got those little hurricane things that come rolling on in every now and then, and we've got environmental sensors all over the place. It'd be very nice to know what's going on, how much flooding is taking place at any given point, what's going on. Traffic, same thing with traffic. There are many, many different situations here where this sort of real-time processing of data, not necessarily really fast data, is needed. But being a professor, that's like practical stuff. So I have to recouch this in terms of something that students would actually get excited in. So what I said to them was instead, I said, okay, let's put this in terms of an interactive art notion, kind of a performance art, a crowd rave performance art situation where there'll be all sorts of inputs from keyboards to Wii Fit pads or Wiimotes like these guys. There could be any number of users, users coming and going. And then you can imagine something like a rave room. We got these big screens all over the place, and the screens are showing the results of whatever's happening. Okay, so people are creating inputs that's being processed and being shown on screens, not necessarily the same output on each screen, okay? So these are 4 students. These are undergraduate students, not graduate students. So the 4 undergraduate CS majors. It's a semester-long project, actually less than a semester because they spent the first 2 weeks learning C# and .NET. So about 12 weeks of work. 4 students. They start with no initial experience in C#, .NET, Azure, Enterprise System, nothing. Okay, they're all seniors, but this is, as you know, for most curriculum, this is way beyond what they would know or see in a regular curriculum. And the other is, if that wasn't enough, the program is set up such that they organize themselves into their teams. They self-direct what was going on. They figure out what they needed to do by themselves. Okay, I wasn't saying they're lecturing them, giving them assignments about do this part next, do that part, another part next. Okay, and it's set up as a discovery process where the whole point is they make mistakes and they understand what those mistakes are. They learn about what mistakes are and how to fix them, and then they fix them. Okay, but I sit there and I let them make the mistakes. So with that, I'm going to turn it over to Christopher, who was one of the leads in the project, and since he actually did the work, it's probably best that he explain it to you.
All right, well, as you know, my name is Christopher, and as Professor Wong already explained, we went into this sort of deaf, dumb, and blind. So we really only had one guiding thought trying to design the system, and that's what does the user want to be able to do, and how should he interact with this cloud, which we just learned about. So we figure, you know, the user wants to connect streams, the user wants to manage those streams, and then since this was a visualization project, he wants to be able to, you know, take these computation outputs and stream them down to some sort of display. So from an architecture perspective, on the ground, what the user is sort of managing, he sees three main pieces. We've got the initial piece, which is the stream manager. This is sort of a wrapper around a stream that you'd want to connect up to the cloud. It provides a way, to connect up to. It has, it can be an arbitrary number of them running around. So while each stream manager might manage, 1 to n streams, you want to be able to have multiple of these spread out wherever you need them. They need not be local to the machine. You also want to be able to dynamically add or remove them. So you need a way to control that. The control panel is the main administration of the cloud functionality and the interactions of the streams. Here is where you're able to take in streams, be they already connected or new streams, tell them how to connect and create basically graphs of computation, and then assign them to endpoints. So from the endpoints, you have the display. Displays, in sort of the way we designed them, are basically powered by commands. So we wanted to be able to say that a display, knows a set of visualizations, but that set of visualizations is not dependent on the incoming stream. It's dependent on basically the parameter types of the command to power this display. So ideally, you have a display that knows a certain set of visualizations, and you can pump in, some streams that match the correct parameters to power it, but then you can also swap out these streams and pump in a completely different set of streams. And as long as you can match up the command type or the data types to the parameters that the display expects to power it, then everything should work fine. And then another thing that we wanted to ensure was that you could hook up an arbitrary number of displays to the same input streams. So, you might want to have one display that's powering by these streams. You might want to have 3 that are all receiving the same inputs. You might want to have 2 displays that have one visualization and then another display that does a different set of visualization, but all powered by that same, stream. And we want them all to be basically platform independent. The user shouldn't have to be using C#, shouldn't have to run .NET, and so on and so forth. So that what was left is then, what do we do in the cloud?
I want to add one quick thing, is that all those 3 pieces are completely decoupled. They're not required to be co-located, and they're not also being tied to a particular home server. They're tied directly to the cloud. Okay? So there are 3 separate decoupled systems.
So then the architecture from the cloud. Well, so Azure provides this notion of roles. And there's basically 3 roles that we 4, but 3 from a computation graph perspective. We have basically the entry points into the cloud for the streams, which we call feature extractors. We have mixers, and then we have the exit points. And so, the problem is that where in a normal cloud system, these roles, each individual instance of that role would look identical. So if one goes down, no biggie, you just transfer it to a completely different instance and everything goes on smoothly because they're all basically copies of each other. But in reality, the way our system is configured, one feature extractor does not necessarily have to be doing the same computation as another one. Same thing with the mixers, So if you bring them down, you need to somehow either redistribute those computation amongst the remaining instances or bring back up, when that instance is brought back up, reconfigure it. And so how do you do that without, how do you do that and with the existing Azure basically recovery that they provide? So we basically decided we needed some sort of persistent storage. And specifically, we need some sort of brain, right? So enter the control process. Control process creates the processing graph. So when you, from the user panel, you're basically talking to this role that's sitting up in the cloud. And what it does is, you're mapping streams to functions to outputs. And then what it does is when you tell it, this is how I want to configure the cloud, it loads up this configuration and then, actually creates the configurations and configures the rest of the cloud up. It's also how the user is able to see the health of the system. So if something goes down, or if streams have dropped off and whatnot, they're able to see this. They're able to pause and resume streams from this control panel because all the stream managers are connected and thus communicating. And it manages the fault tolerance. So as we said, we need some way to recover these configurations. And the way we do that basically is we write up whatever the configuration is into a state repository using Azure storage. We use the tables, and basically we write the configuration down so every instance has an identifier. And it's able to then look into this repository to pull out all the different configurations that it needs to be aware of. And so all the control processor then has to do is communicate to every instance saying, all right, your configuration is ready, go look at it and go configure yourself accordingly. And if you drop, if one of the roles happens to drop, then the control processor can either decide to wait until the role comes back up and retell it to go look at its configurations, or it can redistribute basically the modules inside of a particular instance amongst the remaining roles, and then just needs to tell those roles that have been assigned additional modules to say, you've been updated, go check inside the repository for what you look like now. So now we've got the three main pieces of the actual computation graph. As I said, we have the feature extractors. It is the entry point into the cloud. It does single stream number crunching. So you could imagine, if you're pumping up music or audio data, you would be performing sort of your fast Fourier transform within here. The main purpose, though, of the feature extractor is to convert the incoming stream of data into, basically package it into this data structure we call an event. And basically an event is just a named entity with a timestamp for synchronization. And then it has a bunch of elements, which would be the data elements. And so the events are basically how the user is able to take a stream and direct it around, because he now has this named entity that he can go point to various operations. Specifically, I guess, we have the mixer roles. So the mixers are sort of the stream combiners. They're the ones that will take multiple streams and perform an arbitrary lambda. So we wanted to be able to say, you've got this little module, you've got streams pumping into it, and then you want to perform some sort of computation. You don't care what the computation really is. You just want to be able to pop in a computation at random. And so, although our system, in its current form, only has a preset number of computations, we wanted to design it such that eventually you could, write your own, upload it, and plug it in. So we designed it in such a way that you can give it an arbitrary lambda to operate on. It has a sync barrier, so you define a tolerance, and then using the timestamps, there's basically a sliding window that it goes over incoming events that sit on a queue. And as long as the timestamps are within tolerance, they'll get combined, and then the lambda will be applied onto them. And that will generate then an output event, which it can be fanned out to either additional mixers or to the next bit of our system, which is the display adapters. The display adapters for us are basically just the exit point. They take the event and map them to what we call the command. Commands, are what power the displays sitting on the ground. And so we wanted to be able to say, I've got this event. It has, this integer element. It has this float element. And it's powering this command for the display that takes in this integer element, this float element. So map these elements to those parameters. There's actually, our display adapters can only do this sort of direct mapping. But in reality, you should be able to have, basically an arbitrary different types of display adapters, because really this is just an exit. So if you're not powering a display and you're firing off, completely other different data type, there's no reason why you shouldn't be able to plug these in, which took us a while to figure out how to do. What else? I think that's it. All right, so we have sort of a demo set up, and I'm going to run through sort of how the network is configured in this demo before actually showing it. So we've got basically 3 incoming streams. We have stock values that are ticking up, basically just a name and a price. We've got a level, which is 2 floats that are specifying the min and max of a filter parameter, basically, that you want to see these stocks. You only want to see them between min and max. And then we've got gesture and button detect from the Wiimote. And so what these do is the stock and level pump into a mixer, which will trim off basically any stocks that do not meet the bounds specified. And then the gesture will pump, and then, the resulting filtered list pumps into 2 additional mixers and the display. The display basically is just a table showing you what the ultimate filtered list is. The buy and sell mixers await basically horizontal swipe will trigger the sell mixer, vertical swipe will trigger the buy mixer, and then it'll additionally be shown on the display as a highlighted row, green for sell, blue for buy. Also within the mixers, we've added the ability to fire off an email. So when I do a buy and sell, it'll send off an email which is actually pointed to texting my phone. So hopefully that actually works. All right. Oh, and then additionally, I guess I forgot to mention that the Wiimote is also pumping up and down, so I can navigate the rows by pressing up and down. But as you can see, to minimize sort of things going awry that are out of our control, we have a fake stock stream going, which I guess you all figured out by now, that's running locally on the machine.
Did you know this is the 1 hour in the entire day that there are no stock markets open anywhere in the world? We had live data, real data, but we realized we couldn't run it at this hour.
So hack a little module together and start streaming up fake data. So as you can see, the point to keep in mind is that these are 3 independent streams, right? So as I'm moving this, the only reason that they're getting updated is through the mixers. So let's see, if I do something like raise the min slider up to, say, about 20, right? You can see how it starts cutting off all stocks that are below 20. And then we can lower that one to, say, the max one to about 35. Or 38, 35, well, close enough, 37. Right? And so anyway, so the point is that as he's doing that, the mixer is actually, adjusting the parameters of the filter, and so then the actually resulting filter stream is being trimmed accordingly. So now the other thing that we said we could do is buy and sell. So let me see if my phone actually has any signal. God forbid that AT&T actually cooperate. All right, so if I do swipe, right, you can see that it turned green, and eventually I'll get a text message saying that I've sold the stock at the price that was highlighted. I can also, do here and then swipe upwards. That's a buy, and once more, we can pray, but I don't think it'll work because I have zero signal. Well, if you want confirmation, as soon as I walk out those doors, I'll probably get a series of text messages. We can confirm whether or not I was lying or telling the truth.
You can also overload his phone by just shaking the Wiimote around.
Well, yeah, during testing, that's exactly what happened. You forget that this thing is running, and you end up getting something like 100 text messages. But I think the point to keep in mind is that these are 3 separate streams, and although for the demo they're all running locally on my machine, there's actually no reason for them to have to be running on the same machine. I could be plugged into the machine with the Wiimote, the slider could be coming from someone else's computer, and then the stock stream could be live if we weren't in this black hole of stock trading. And the ways that the displays has all these inputs coming from it, and these continuous streams are being combined and acted upon by these various mixers that we've set up.
Just to prove that we could do it, the display is actually a Java app. It's not a .NET C# app. It's a Java app that's connected directly up to the cloud.
Yeah, from the displays, we decided to use JSON because it's a very easy it's very easy to map languages to elements to parameters, since JSON is basically just an object, and it's platform neutral. All right, so obviously we didn't get to this system without some fire and brimstone in the way. There were definitely challenges because, as we went through this, we really felt that the cloud does offer the ability to do this type of stuff. Certainly we've got more work to do before it's feasibly usable. But in its current form, Azure has a few obstacles that we felt need to be addressed. One is a TCP timeout. So the load balancer does not expect persistent connections, right? Because it's meant to be sort of batch style processing. You submit a job, it gets it, and then it pumps it off and then sends it back to you. So if you're doing a persistent connection, but you're not sending data fast enough, the load balancer will actually terminate the connection. So if you're sending data at under an element a minute, you'll actually get the connection itself will be cut off. And so the way we got around this one is to implement basically a pinging subsystem in the network layer, and that pulses about every 20 seconds or so, just to make sure that all the connections stay live and aren't terminated. Another difficulty was developing. The dev fabric, while fairly nice for actually debugging, what is the cloud, is restrictive in that it does not allow you to make external connections. This is problematic when you're dealing with a system such as ours that has multiple pieces running to it. And I believe this is me getting my promised texts. Yes, I have 3 texts that I bought stock, so I know you can't really read it, and I could be making it up, but it works. All right, anyway, so back to what I was saying. So yeah, for example, we've got displays, and we've got stream managers, and they all want to connect up to the cloud. And you can't do that on the dev fabric unless you're running everything on the same machine, which gets burdensome. Additionally, ways around that, you could either tell the cloud to connect downward, but the problem there is, well, I'll explain later for the lost connections. Reconstruction of lost modules. So as we said, right now Azure says, if an instance goes down, we'll bring it back up, no problem, which is fine if they all look alike. But if they don't, you need to somehow tell it to reconfigure itself. We use the Azure tables to do so, but it'd be nice to have a little help from the actual fabric itself rather than trying to implement our own system. Finally, we've got the problem with lost connections. So the load balancer, again, because it's built under the assumption that every instance is identical, will automatically just round robin assign a new connection to an instance. But really, you want to assign it to a specific instance, specifically from like the feature extractor end. There's one feature extractor instance with the right feature extractor set up, and you want to say connect to this one. So it'd be nice to be able to say, yeah, I know I have these instances, connect to that one. Because otherwise, if you want to, the other way is to say cloud connects down, but if you do that, then there's added complexity because you've got to make sure your ports are configured properly. You've got to make sure firewalls are all configured properly. We couldn't run the demo today if we were connecting down because we don't have access to the ports to listen on. And yeah, so these are the biggest challenges that we face designing our system. But we feel that there could be some work done that would actually allow this to become quite feasible and quite easily done. That's all. Questions?
One thing we didn't have time to show you all today was how we are dynamically building the feature extractors and the mixers and the views adapters up in the cloud. Those are not preset, okay? Those are actually built at runtime. We allocate where roles, the roles are being dynamically allocated, everything's being dynamically allocated up there, okay? The user interface at the moment for that is a little less intuitive. Dennis, if you're listening, who's listening down at that
live stream,
that other search company down in Silicon Valley, that part needs a little bit of work still. So it's not. We didn't want to show it to you because it's not obvious of what's going on with that. But is very distinctly what this is not set up where we create the whole network on the ground and then ship the whole thing up. It's created up in the cloud already, okay?
Okay, thanks very much. So let's thank our speakers. So we have time for some questions. There's one couple right there.
Wow, that's a very sensitive mouse clicker.
Hi, Barak from USC. When you describe your system, it seems very similar to the Microsoft Stream Insight, which now you can have either on cloud or off cloud. Have you considered using it? Is this architecture that is the underlying architecture? Does it have any connection to Stream Insight?
We came in knowing absolutely nothing about the cloud, so we sort of, built it under this option. We haven't looked at many of the new technologies that come with. We built this 6 months ago.
This is built last fall.
I can add that Stream Insight is actually a product related to our database system. It does not yet use the cloud, and so there's a cloud experiment. They're very similar in spirit, but this is the first time I've seen anything like this on the cloud.
Right, because we really wanted to build this up in the cloud.
Other questions?
Yeah.
Yeah.
Mike Franklin. So one thing about stream processing is it's very sensitive to delays, right? Because data is being pushed in, and if you're not able to react in time, you end up with losing data or other bad things happening. One thing about moving to the cloud is you lose control over your resources. So I know this was just a one-semester project, but have you thought about how you'd handle doing this in a virtualized environment? Is it just over-provisioning, or is there more you can do?
We had started thinking about how to do it, but considering that this had been the first time we were even involved in a project of this size, there were several other obstacles that kept us back.
I forgot the speaker from UVA earlier this morning actually put up some numbers with the latencies on them. And I was furiously writing those latencies down because I'm about to march back to our IT department and say, how come I can't get these latencies? Because we were looking at latencies that were jumping from 20 milliseconds to 200 milliseconds and back and forth, and which is why we didn't try to hit audio speeds in our, and I think because the latencies were killing us. But absolutely, that's a big problem. It's not clear to me, I mean, particularly since I saw those latency numbers this morning, how much of that is due to our local infrastructure versus actually up in the cloud. We couldn't isolate where these problems were occurring as to what the order of magnitude of the problem was, okay? Because they were jumping around so much. The system is built, however, to be able to handle within the speed that it can handle the data, to handle whatever the latency come in. That's why their feature extractions translates the data from just sort of this raw data stream that's coming in into these events. Okay, that way the events can come through, since they're all time tagged and whatnot. They can pretty much come in whatever order, and essentially what the mixers do is they put them into a priority queue, which reorders them as they come back in, and this sliding window comes along with this tolerance, and so that gives us a lot more insulation against these problems. Certainly, if you get such a hiccup that it's so long, we were just at this stage, we're pretty much running on the assumption that if data was unrecoverable, that we would just drop it and just keep going. That we were really trying to look at sort of the stream notion and not really worry about having to keep every single piece of data that was coming along, but more just whatever's coming along, we would try to process them as they came. And the sliding window technique with the events gives us a fair amount of management on that.
Okay, I think at this point we need to move on to the third speaker in the session. Tevfik, you ready to come on down here? And thank our speakers once again. Very nice talk.
Sure.
You have yours on the machine?
Yes.
Great. And you need to take your badge off.
Here, let me jump in there for you. Put this microphone on right. No, wait. This one right here.
So we're waiting for that. Just say that Tevfik is from State University of New York, and he's going to talk about the Stork data scheduler. Again, Windows Azure. I should note, by the way, those of you that are wondering, why are there so many Azure presentations? And we actually didn't bias the selection towards that. There may have been some bias by the submitters as to what we might want, but anyway, we're happy to see these projects using Azure.
Good afternoon, everybody. Can you hear me well today?
He has to go up in the room.
Okay, I think it's on now. And today I will be talking about the Stork data scheduler, which has been around for a while now to mitigate the low-level data handling bottleneck of data-intensive applications. And through a recent NSF grant we have received from Computing in the Cloud program, we have been now porting most of the Stork functionalities for data scheduling and data management to the Windows Azure environment. Today, most of the speakers have already talked about the increasing data requirements of scientific applications and the so-called data deluge, so I don't want to repeat them, but these increased data requirements have been also reflected in the strategic planning documents of federal funding agencies as well as many private sector companies. And in each of these documents, we see an increasing need for taking care of these low-level data handling issues. And I especially would like to highlight one of the quotes from the DOE's Office of Science report on data management, which says, in the same way, the load register instruction is the most basic operation provided by a CPU, so is the placement of data on a storage device. So it is therefore essential that at all levels, data placement tasks to be treated the same way the computing tasks are treated. So as you know, historically, the data placement tasks, data movement, and data storage has been considered a side effect of computation and a kind of second-class entity. And starting from my work I have done in my PhD thesis, we have been trying to change this and make data placement, data movement a first-class entity in distributed computing and cloud computing environments. And we have done a bunch of work to bring this data awareness concept to different levels or to different tools in cloud computing, distributed computing, involving the scheduling, storage management, workflows, and resource allocation, and so on. And today I will be mostly focusing on data-aware scheduling, but we have done a lot of work in almost in all of these areas, and I will be glad to discuss our other work in these areas after my talk. So what do we really mean by data awareness in scheduling? So assume you have a bunch of sites between which you want to transfer large amounts of data. And these sites can be different data centers as well as individual nodes in data centers between which you want to transfer some data, either for replication purposes or for further processing or for longer term storage. And of course, there can be some external sites as well, such as the researcher's home institution, where actually the data is generated, or where the data, or where the process data is sent back, and so on. And at any time, there can be hundreds or thousands of files being transferred between these sites. And this needs to be coordinated, scheduled, and managed in order to provide high performance as well as efficient resource utilization. And when I talk resource utilization, in this case especially, we are more interested in storage resource and network resource utilization. So there are different policies a data-aware scheduler needs to take care of or needs to consider. So this includes where to place data, and in making these decisions, it can use both the physical and semantic contents of the data. So it can try to put semantically close data sets close to each other to improve the performance. It needs to consider how to order these requests, considering there are hundreds or thousands of requests, and especially when the bandwidth or the storage capacities are limited. These requests need to be ordered in a way to optimize the utilization of these resources. The best transfer protocol should be chosen, especially in the case where multiple protocols are available between resources. And this protocol needs to be tuned or optimized for better performance, and so on. And we have implemented the Stork data scheduler a long time ago as one of the first prototypes of these data-aware schedulers. And as of now, it has been very widely used by national and international institutions in different areas of science to take care of low-level data handling issues. And it has been funded by NSF through the 3 different programs, including Career, STCA, and the recent CIC program. And the main features of the Stork data scheduler includes early error detection. Before actually the errors happen, it tries to detect any possible errors and try to fix them. Error classification and recovery, which is especially important when you need to retry or recover from failures, whether it's a permanent versus a transient error. Aggregating data transfer requests and caching connections, supporting multiple transfer protocols, especially important in heterogeneous environments, dynamically tuning and optimizing data transfer protocols, and end-to-end throughput and prediction and optimization services. Support for heterogeneity is especially important in distributed environments. Since different users may prefer different protocols to transfer their data, and a data scheduler like Stork needs to basically understand and talk each of these different protocols. But it becomes more and more complicated, especially when the protocol that the user wants to use in their home system does not really match with the protocol which is available in the cloud environment. Of course, you can always deploy protocol services as applications in the cloud, but in many cases there would be some need to translate between these different protocols, and we would need a capability or an intermediary which would perform this protocol translation between different services in case some of these services are not available in the deployment environment. And the transfers may fail due to different reasons. As you know, the server can be down, the service is not running, or in some cases the file even does not exist, or there can be some authorization authentication failures, there can be DNS or network errors and so on. And what important in this case is how to first detect and then classify this type of failures. So the Stork data scheduler can first run a series of benchmarks to detect the errors before actually they can happen, such as checking the DNS and the protocol services, whether they are up and running and so on, etc. And afterwards, classify the errors, whether they are transient or permanent failures, so that it can either continue retrying or it can return to the user with the exact description of the error, so that the user can involve and fix the error. One of the most important features of Stork Data Scheduler is what we call end-to-end data throughput optimization. So when we consider an end-to-end system, so you want to transfer some data from the disk of a resource to the disk of another resource. There is a path in which the data transfer takes from the disk to memory and memory to network card and over the network and so on. And if you want to optimize this end-to-end throughput, optimizing the network is not sufficient. And I will show you some examples why. Especially in the morning, we had some questions about network being a bottleneck and how to deal with network limitations and so on. But if the end systems are not provisioned well, even though you increase your network capacity, it will not help to increase your overall end-to-end throughput. So I will show you three slides which would explain in which levels there can be some bottlenecks and how they can be removed. So the first slide here shows the case where the network protocol can be the bottleneck, and this bottleneck can be removed by optimizing or tuning the network protocol. And in this particular case, so we have three different graphs for three different network settings: a statewide optical network with 10 gigabit per second backbone, a nationwide optical network with 10 gigabit per second link, and an intra-cluster network. And as you see, when we start with an unoptimized transfer using a single stream and unoptimized buffer size and so on, we would get a very low performance from this big fat network. So around 600 megabits per second from a 10 gigabit network, it is around 6% of the available capacity that we would be getting. And one of the traditional ways of increasing the performance in such cases would be increasing number of streams would get you to a point where you would be getting around 1 gigabit, but you cannot really get beyond that point by just optimizing the protocol itself, since the bottleneck can be somewhere else, such as the disk system. So if the underlying disk system does not provide you more than 1 gigabit per second bandwidth, then there is no way you can increase your throughput. And in the second step here, we test how this disk bottleneck can be removed by basically using multiple disks. And the physical limitation of this would be basically when you use no disks, correct? So when you use basically memory-to-memory transfer, it would show you the physical limitation of your system. And this is what we test here. When we do memory-to-memory transfer instead of disk-to-disk transfer to see the limitation, we see we can get up to maybe 7 gigabit per second in the statewide and around maybe 5 to 6 gigabit per second in the nationwide network. Now, the third step would be, so we increase the protocol and the network utilization, we increase the disk utilization. The next step would be using multiple CPUs to actually remove the CPU bottleneck, since once you have optimized disk and network utilization, the next bottleneck would be actually the CPU. And this can be, again, removed by using multiple CPUs. And as you see, we can, after optimizing 3 of these systems, we can get up to 9 gigabit per second, which is very close to the physical limitations. Now, the question is, of course, these tests show where the bottlenecks are, but it doesn't show how they can be optimized. Okay, and the answer would be increasing this, basically optimizing these 3 parameters: number of streams, number of disk stripes, number of CPU nodes. Correct, and of course, these disks and CPUs can be hosted as services in the cloud, infrastructure as a service, and the network bandwidth it could be increased using multiple parallel streams and buffer size tuning and using some other mechanisms. And what we do in Stork data scheduler is we convert this problem into end-to-end flow model. Okay, where we have the CPUs, the disks, and the network cards as nodes. Okay, and each of these links between disk and CPU and network card and so on, they can have different bandwidths. So what differentiates this model from a traditional network flow model is in 2 aspects. First, the available capacities in these links, they are not constant. Okay, so we don't assume a constant network bandwidth, since there can be multiple users using the network, and the available network bandwidth can change over time. So this makes the problem a dynamic flow problem. But also, one of the nodes here is not really a traditional node in a flow problem, since we have CPU as part of the problem, and it's not really very straightforward to convert CPU capacity or CPU utilization into throughput. Okay, these are the 2 aspects we focus on this particular problem. Now, the first, how to deal with dynamic network bandwidth limitations, and how to increase optimize the throughput utilization. So there are different ways, and there are different parameters that you can optimize. Number of TCP streams, for example, if you are using TCP, the buffer size, the IO block size, and so on. And I just want to focus on the number of streams in this particular example and how we do that. So you can simply assume, okay, I increase number of streams and my performance or the throughput I get would increase. And this can be true until a certain point. But what we observe in many cases is until you reach a certain point, you would get to a saturation, and then your performance will start decreasing since you will start pushing more and more packets to the network. Okay, and the question in this optimization is how to predict this peak point and use this in your scheduling decisions. Okay, so there are some existing models and which mostly assume when you increase the number of streams, your performance would increase, assuming no congestion, and when there is congestion, it would stop increasing and come to a threshold and so on. But none of these models can actually be used to predict the optimal number of streams, which we see in this particular case right here. So we have developed a bunch of different models to capture that behavior. And just to emphasize, this graph is just an example, and this graph can change basically from one transfer to the other, based upon your source, destination, nodes, as well as your network settings and so on. Okay, so we are looking for a generic model which would be able to apply it to all different cases. So I will not go into details of different models, but in especially two of them, one is based on what we call Newton's iteration, and one is based on full second order polynomial. So we generate a function which can relate the number of packet losses to the number of streams, so that we can actually predict the effect of parallel streams on the TCP throughput function. Okay, I just want to show you a couple of examples on how well these models, especially the Newton's model, can predict the throughput graph. The red graph here, you see it's the actual curve. If you would perform, the transfer using different number of streams, but of course we want to predict it without performing those experiments, correct? So we want to predict it with the least amount of prediction overhead, and in most cases we can predict it with as little as 3 samples, and each sample can be less than 1% of the actual transfer. Okay, and so this brings very little overhead to the system, which I will show in a different graph. But also, what we do is to further optimize this. These samples or these samplings, it can be done as part of the actual transfer. Basically, instead of just doing random sampling with some dummy data, we use the actual data in these samplings so that actually they contribute to the actual data transfer. Okay. Here, the green graph shows the prediction by our model, and the blue line shows the prediction by the second best model by others. Okay, and the first graph is for local area network with very low bandwidth and low latency, and the second graph again very low bandwidth but high latency. Here the third graph shows a statewide network with 1 gigabit per second network bandwidth capacity. And the last one shows, again, a statewide network with 10 gigabit per second. So different settings, and in each of them, the actual graph, it looks different but using a similar behavior in terms of first increase then decrease type of behavior. And we can do very, very good predictions, especially when we consider our goal is to predict the peak point here. Okay. Now, that was only one component, predicting and optimizing the network throughput. And one of the other important components is, as I mentioned, how to make the CPU utilization part of the problem and its translation to throughput optimization. And this, as being not straightforward, we have observed that there is a very high correlation between, again, number of streams used in transfers and the CPU utilization on both the server and client sides. And we use a regression analysis technique to actually map the CPU utilization to a throughput graph. And this allows basically a one-to-one translation between CPU utilization and the throughput graph. And finally, what we do is we use this information in advanced reservations. So reserving these links in advance. Again, what we do different from existing approaches is assume we have these predetermined reservations. So this link has reservations for 900 megabit per second and 700 megabit per second. So this graph shows the existing reservations, and this shows the remaining bandwidth. So the existing approaches would allow you to make a constant reservation over time, such as, let's say, 100 megabits per second for 13 time steps and 500 megabits per second for 7 time steps and so on. Okay, but what we want to achieve is we want to be able to make a continuous reservation, but with different bandwidth capacities. And the data throughput estimation and optimization capability provided by the model I have presented, it allows us to control the amount of data we send over the network so that we can actually have a changing reservation over time, and we can continue the transfers without any interruption. So we don't need to start and stop here, but the amount of data sent over the network changes by dynamically reducing number of parallel streams, for example, over time, or by dynamically reducing the available disk and CPU resources for that particular transfer, and so on. And these models and prediction algorithms, they have been implemented in the Stork data scheduler. And this provides the users two types of services. One is the estimation service. Basically, the user can say, okay, I want to transfer X amount of data between these resources and these destinations. So give me the amount of time I would need to transfer this data, as well as give me the optimized parameters to be used to transfer this data, and what would be the change in time and so on. So by using minimal sampling overhead, the scheduler returns to the user the amount of time it would take without optimization, with optimization, and the optimized parameters and so on, without actually performing the actual transfer. And the second type of service would be making the actual transfer. So the user can say, okay, I want to transfer this data between these resources and just transfer it the fastest way, or giving different policies such as using least amount of resources and so on. Okay, and this graph showing the overhead of optimization. The purple line here showing the non-optimized time the green line showing optimized time, red line showing the overhead. Okay, and the overhead plus the transfers, together it takes much less amount of time compared with the actual transfer time. Okay, so wrapping up, so all of us know the scientific applications has been getting more and more data intensive, and data sharing and I/O has been one of the major bottlenecks. And in the Stork project, we have been focusing on developing models, algorithms, and real-time systems to overcome or mitigate these bottlenecks. And through our recent CIC grant, so we have started porting all of these capabilities in the Stork data scheduler now to Windows Azure environment. So this is the Stork web page from which you can get more information. And I would be happy to answer any questions.
I think everybody must be ready for a break right now. So, Tevfik, are you going to be out there available?
Sure. Yeah.
No questions?
I can take questions after.
All right. Thank you very much. Thanks, everybody, for the session. Thanks.